In this class, let us learn about spanning trees and fundamental circuits. First is spanning tree. If G is any connected graph, okay, and I'm taking a tree with respect to this graph, which is a subgraph of this graph, and it contains all the vertices of G. I'm taking a tree which is a subgraph of G, and this contains all the vertices of G. Any tree T is said to be a spanning tree of a connected graph G if T is a subgraph of G and T contains all the vertices of G. Okay. It must be a subgraph of G and it should contain all the vertices of G. Then I can say this T as a spanning tree of graph G. For example, if this is my graph, A, B, C, okay, sorry, D. Okay, then this is my graph. With respect to this, it's not necessary that it should have one spanning tree. In fact, it will have at least one spanning tree will be there for every connected graph. Okay. For this, I'll draw one spanning tree which contains all the vertices of G. Okay, A, B, C, D. This is one such spanning tree which is a subgraph of G and it contains all the vertices of G. Another one I can draw like this. I can even consider this B, A, C, D, which contains all the vertices of G, like that. Okay. So always remember one thing, every connected graph has at least one spanning tree. One spanning tree will be there for a connected graph, and if the graph is disconnected, then it will have spanning forest. Forest means collection of trees. So if graph is disconnected, then it will have a component. With respect to the components, I'm taking trees which contains all the vertices of G, so that it will be a set of trees which has all the vertices of G. So such set is nothing but spanning forest. So in a spanning tree, if these edges are called branches of tree. An edge in a spanning tree is called branch of tree. Branch is nothing but an edge in a spanning tree. An edge in a spanning tree is called branch of a tree. And an edge in G which are not in the given spanning tree is called chord. An edge in G which is not in the given spanning tree, okay, with respect to particular spanning tree, okay, in the given spanning tree is nothing but chord. Branch means an edge in a spanning tree, okay. An edge in G which is not in this given spanning tree is called chord. For the same example, if I consider with respect to T1, okay, these two edges are the chords, and these are the edges. I'll give some other example in the same way, but I'll name the edges. Suppose this is my graph. One, two, three, four, 5 vertices. A, B, C, D, E, F. Now this is my G. I'll draw one such spanning tree. Spanning tree is a subgraph of G which contains all the vertices of G. 1, 2, 3, 4, 5. Now A, C, E, F. Now what are the branches? Branches are nothing but edges of a spanning tree. So A, C, E, F are the branches, and chords with respect to this spanning tree is D, then one more here, that is B. Okay. Now, distance between two spanning trees. If I have two spanning trees, then what is the distance between them? That is number of edges in G which are present in one spanning tree but not in the other. I'll explain with an example. Distance between two spanning trees is nothing but the number of edges of G which are present in one tree but not another. Not in the other. Not in the other. Like suppose if I have a graph, say this is my graph. Yeah. This is my graph G. Name the edges A, B, C, E, F, G. Okay, this is my D, E. Let it be, no problem. Yeah. Then I'll take a spanning tree with respect to this graph. Okay. Now this is my spanning tree. G, B, C and F. And another one is, I'll take it like this. One more vertex should be there, no? Yeah. Now this is A, this is C, this is E, this is F. This is T and say T dash. Now distance between T and T dash is nothing but number of edges of G which are present in one tree but not in this. Okay, say if I consider this G, it is in this but not in this, so I can take 1. And this one is already in this, so I cannot consider. Here the edge B which is in T but not in T dash. Therefore number of edges of in G, one is this and another one is this. Is there any edge? F here also it is there, this also it is there. So distance between them is 2. In fact, it is nothing but this distance between the spanning trees is nothing but number of edges in T ring sum T dash. We have learned operation on graphs. Same thing, I'm considering two subgraphs. Okay, number of edges in T ring sum T dash divided by 2 gives me distance between two spanning trees. Next is rank and nullity of a graph. Suppose I have a graph G with n vertices, e edges and k components. Then rank of a graph is nothing but n minus k, and nullity denoted as mu is nothing but e minus n minus k, which is nothing but e minus n plus k. Rank of a graph is n minus k and nullity is e minus n plus k. This is for a graph with n vertices, e edges and k components. This is if graph is disconnected. If graph is connected, then the number of component is 1. Okay. Next term is fundamental circuit. Fundamental cycle or circuit. Fundamental circuits. A circuit which is formed by adding a chord to the spanning tree is called fundamental circuit. Chord means it's an edge in G which is not in the given spanning tree. Okay. So for the spanning tree, I am adding one chord so that it will form a circuit, and that circuit is nothing but the fundamental circuit. It's a circuit formed by adding a chord to the spanning tree. Is called fundamental circuit of a graph with respect to the spanning tree, because there may be more than one spanning trees. Okay, with respect to what spanning tree, this becomes a fundamental circuit. That matters. Okay, suppose this is my graph as I have taken earlier. Okay, now I am drawing a spanning tree, one such spanning tree. So this is my spanning tree now. So with respect to this spanning tree, I am adding an edge to get a fundamental circuit. So if I add this edge, then I am going to get this circuit. This is the fundamental circuit with respect to this spanning tree. I can even add here so that this will be a spanning tree. Next is cut set. In a connected graph G, cut set of edges means it's a collection of edges. If I remove those edges from graph G, then graph G becomes disconnected. It's a set of edges. Okay, if G is a connected graph, cut set of edges is a set of edges whose removal from G leaves G disconnected in such a way that, always remember, in such a way that no proper subset of this set will disconnect G. Okay, leaves G disconnected provided removal of no proper subset of these edges disconnects G. Okay, it's a set of edges whose removal from G will disconnect G, and no proper subset of this set will disconnect G. Suppose I have graph for this graph. Say if I delete two edges, then the graph will disconnect, of course. So if I delete an edge A and an edge D, if I remove this, then will that disconnect the graph? No. If I remove A and B, yeah, of course. So this is one such set. This is also a cut set now, A, B, and if I consider A, D and C, A, D, C. No, if I delete only A and C, then it will not disconnect the graph. If I delete only A and D, it will not. So A, D, C, this is also one such cut set. Okay, it's not necessary that it should have these many cut set. It may have many more. So this is for the simple example. You can even try for the graph, just something like this. Say I'll add a self flow. I'll name the edges A, B, C, D, E, F, G and H for the self flow. Now one such, you may be asked to find all the cut sets of a graph. Okay, so first one, singleton set. Is there any one edge on removal of that the graph will be disconnected? That is edge A. If I remove that, then the graph will be disconnected. Then set of two edges, if I consider, if I delete B and E, similarly B and C, then C, D, F, I can delete C, D, F. Here two set, one more F and G. If I delete, then also graph will be disconnected. Then C, D, G, C, D, G. Then F, G I have already done. D, E, G will also disconnect. Yeah, one more is there here, C and E. If I remove C and E, then so another one, B, D, F, B, D, G I have already written. No, B, D, G. Like that you can write the cut sets for G, for a given graph G. It's a cut set is a set of all edges, set of edges on removal from G. G will be disconnected and no proper subset of this set will disconnect G. There is a theorem says every cut set in a connected graph G must contain at least one branch of every spanning tree of G. Okay, we know what is cut set, we know what is spanning tree, and we know what is branch. Now consider a spanning tree in a connected graph G. let T be a spanning tree in a connected graph. Okay, let T be a spanning tree in a connected graph G. Now let S be any cut set in G. Let S be any cut set in G. I have to prove this cut set should contain one branch of every spanning tree. Okay. Now suppose this S does not contain any edge of T. Any edge of T is not an S. Then this T is contained in G minus S. If S is not having any edge of T or any edge from T, then T is in G minus S, right? Suppose S does not contain any edge of T, then T is contained in G minus S, right? If S is not having an S is a cut set, means removal of the edges of S from G will be disconnected, okay? If this is not having any edge in common between this, there is no edge in common between these two, then T is either G minus S or it is contained in G minus S. In fact, removal of this edges from set S will disconnect G, which is a contradiction. If see what happens if I remove S, then it will be a disconnected graph. Then how can it have tree? Right? Tree means it should contain, it's a spanning tree. Okay, so it should contain all the vertices of G. Right? If I say that T is in G minus S, what is G minus S? In fact, it is a disconnected graph. Since S is cut set, so this is a disconnected graph. How can I say that T is in G minus S, which is a contradiction? Therefore, this S must contain at least one branch of spanning tree. Okay. Removal of S from G will not disconnect the graph. Which is the contradiction. Therefore, S must contain at least one branch of spanning tree. I repeat, I am taking a connected graph G and I am taking a spanning tree T of graph G and I am defining one such cut set, say S. Okay. If there is no common edge between these two, S and T, then T must be in G minus S. Means after removal of S edges from G will not be disconnected if this is in this. Why? Because, see, this is a spanning tree. It should contain all the vertices, right? How can it be possible? That's the contradiction. So, S must contain an edge, at least one edge in common to spanning tree.